This will go. Physics of my own. I have not yet.
So it will go.
Okay, good afternoon, everyone. Today we are very happy to have Riccardo Rattazzi from EPFL. And while he's worked on a variety of things, today he's going to tell us about the quantum mechanics of Fock. I think to it.
Yeah, this is a subject where somehow I started to work. I mean, I took it as a hobby, okay, and as it sometimes happens with hobbies, at a certain point it became an obsession. And okay, today I will show you where that obsession has taken me. So as I'm a particle theorist, interested in the standard model, what lies beyond, I think I owe you a little explanation of how I ended up here, a little story. Well, first of all, let me tell you who are the people I collaborated with here. They should be here, right? Should be this.
Click in the window.
It wouldn't?
Try clicking in the window to activate that.
Oh, yeah.
I have to click on the window.
Maybe because of some PDF. It was like that.
I think I can go like this. Okay, I think I can go like that. So these are the people I collaborate with. This all started with a paper I wrote in 2005 with Dubovsky, Gregoire, and Nicolis. At the time, we were thinking about cosmology and conditions under which in cosmology the null energy condition is satisfied. And it's there that this issue of the quantum perfect fluid emerged. And we then wrote a paper in 2005, 10 with these people were first the obsession started. And okay, apart from other things, what I will talk about today is largely based on the collaboration, I can say aborted collaboration in 2015 and 16, 14 and 15 with Solomon Enlich, Walter Goldberger, and Ira Rothstein. Essentially, we were not entirely convinced of what we were getting, and at a certain point we lost interest and we stopped talking to each other. No, we were talking to each other. No, we're still friends, okay? Talking to each other about this, okay? And in 2019, I resurrected it. At EPFL, we always have to find out project for master students, and I said, well, why don't you go back at this? And my student, Orlando C, who is now at Harvard doing his PhD, and Andrei Khmelnytsky, fortunately quit physics. We wrote a paper in 2020. After that, I'm now in the sort of course of trying to understand other aspects. I think within some time, maybe a year, I think I will have a different story of this business. But since I'm still in the middle between the old story and the new story, I'll give you the old story, and then in case I will comment. Okay, so why did I end up working this? So let me give you a little thing. So what is cosmology? So originally, as I said, we were thinking of cosmology. So what is cosmology? Well, what is cosmology? You can answer in the following way. Think of the basic Einstein equation that governs cosmology. And there are two sides to this equation. One is the dynamics of space-time, if you want, gravity. And the other is source, the energy momentum tensor that propels cosmological evolution. And in cosmology, this mu nu is originating from stuff that fills space, okay? That is to say, a quantum field theory of finite density, or if you want, condensed matter. So in the sense, the connection between, so cosmology is gravity playing with condensed matter. Okay? In fact, this connection is already, the connection of gravity and condensed matter is already commented on in a paper that Anderson wrote in 1962, the famous paper on the plasma mass. Anyway, so it happens that at least in the early universe, but at every stage, at some length scale, you can treat mu nu as a homogeneous isotropic background, okay? Which is to say a finite density QFT, which spontaneously, if you want, breaks Poincare invariance down to translations and rotations. And the dynamics of the medium is characterized by the fluctuations around it, which, to say, the hydrodynamic modes that are largely dictated by the symmetry breaking process. Okay, Poincare broke into ISO3, in the sense the hydrodynamic modes are largely viewed as the Goldstone bosons of the symmetry.
Question? So the expanding universe is a time direction associated with it. So I'm surprised to see Poincare there.
Yeah, I'm focusing now, okay, on like in all situations where you have some degree of freedom, like say gauge degree of freedom, that let me say it this way, at short distances, you can view this as the association. So I'm going to show this. So let me say it this way. Think in terms of particle physics, a similar situation is the one where you have on the left-hand side the dynamics of the W boson, and on the right-hand side the source associated with the Higgs sector. At sufficiently long distances, which is to say at distances of the order of the W mass, they're very intertwined. But at shorter distances, you can treat them independently. Okay, you can treat, like here at shorter distances, we can treat the propagation of sound waves, the perturbation of the medium, forgetting gravity. So the short distance dynamics is that's it. Okay. So so what is model building? Model building, which is the activity of people like me, is in a sense exploring the space of possibilities in quantum field theory to see what is possible and what is not, and what can happen. Okay, particularly what are the options for the dynamics of the early universe? And as I said, at short enough distances, this source here can be viewed as a quantum field theory in a state which realizes this breaking, and its dynamics is characterized by the soft modes, or if you want, the hydrodynamic modes or the Goldstone modes around it. So I think it's an interesting endeavor to explore what possibilities you have for that. So classifying these options. Okay? And this game was played in the early 2000s when the community was trying to understand what possibilities there were for the cosmological acceleration other than just a bare cosmological constant. This was the so-called attempts to modify gravity in the Fred, which in the end, it amounts to coupling gravity to some often very peculiar and degenerate finite density system. Okay. So in the end, classifying what can happen is what was interesting. So in a sense, and this question for the dynamics behind mu nu can be phrased as the question: what are the space of sensible EFT, effective field theories, that realize the spontaneous breaking of the Poincare group down to ISO3? Again, this at the level, if you want, at distances shorter than the curvature, where you can just look at if you want, at these hydrodynamic modes, such that their coupling is not yet important with gravity. Okay. So this was the exercise that essentially was being done when considering modifications of gravity. And so we wanted to understand these options, okay? At least it would have been nice in this respect to understand at least the simple ones, okay? To really see what makes sense, what doesn't make sense, but at least you should test this program, at least on the things you think you should understand, okay? And it is in the process of this little exercise that I get, and that I stumbled on this little obsession that I want to talk about today. So let me give you, and you get to this, if you want, to this case right away, okay? And so in order to illustrate the question, let me give you the first example, the simplest possible example of this, okay? Which is something we understand. In fact, Son is the person who understood this in this language, at least first, because there were also previous papers without relativity, but nonetheless, this Is there on paper? So so let me consider the simplest possible example of a finite density relativistic system is the relativistic superfluid. So what is the superfluid? So the superfluid, I think I presented it in the wrong way here. Okay, it's okay. So the superfluid is, I should have written this above. I don't know why I ended up here. So the superfluid is a particular, it realizes a particular pattern of breaking of Poincaré. Okay, it realizes the breaking of Poincaré times the internal U1 quantum number down to translation and rotation, and times an effective time translation, which is nothing but a linear combination of the original Poincaré time translation times the internal charge, the internal U1 charge. Okay, so how is that realized? It's realized by having a scalar field. Okay, so to realize a symmetry breaking, you need, like in the pion Lagrangian, simply to realize an effective Lagrangian for it, you construct, you find out what is the minimal set of degrees of freedom that realizes this, and these are the Goldstone bosons, and then you assume that there's nothing else like. And this allows you to write, and then there is a standard technology for writing the effective Lagrangian for that. Okay, so in the case of space-time symmetries, unlike for internal symmetries, the number of the Goldstone bosons dictated by the symmetry breaking, or Goldstone soft degrees of freedom, if you want to say it a different way, is not the same, they're normally less. And in this case, you just need one, okay? And so to realize this situation, you just need a scalar field that shifts under the internal U1. And in this situation, you have, so the scalar is derivatively coupled, and for the derivatively coupled scalar, there always exist solutions of the equations of motion that depend linearly on the coordinates. Okay, and the situation we are interested in here is the one where the solution linearly depends on time times a coefficient which ends up being identified with the chemical potential plus the fluctuation. Okay, so in other words, you have roughly a scalar that behaves like a clock. Okay, where wherever you are and whenever you are, you can ask what time is it. It's like asking what is the value of the scalar. Okay. What is the value of phi? So you have a cosmological clock. And at the leading order in the derivative expansion, because we're doing effective field theory, so the idea is that we have some short distance physics, and now we're doing physics long distance, and there's going to be some effective dynamics and effective Lagrangian, which is organized in a derivative expansion. So at the leading order, you consider terms in the Lagrangian that have the minimal number of derivatives per field. Okay, and in this situation, there's only one invariant that you can write down, is this. Okay, so the Lagrangian will just be a function of this invariant, and the physical properties of the resulting fluid, like the equation of state, the relation between charge density, energy density, and pressure, are all codified by this function. So this function contains the notion of the equation of state. So it's a function, okay? But once you know this function, then you know at leading order. So then the interactions among waves, okay, the fluctuations from the phonons are obtained by expanding this function, okay? So the derivative of this function, which you presumably you can measure in some experiments, all the higher derivatives. So this function itself controls at leading order all the multi-leg correlators for the fluctuation. So in other words, controls the soft phonon scatter. So there is a one-one correspondence between the set of scattering amplitude for phonons and the equation of state. I mean, this is just a generalization, if you want, of what you have in the pion Lagrangian, where there is one quantity, the pion decay constant, but it's not a function. It's slightly more constraining, which controls at leading order all the scattering between pions. Okay, and then of course you could refine this by having higher derivatives and so on, like in all effective Lagrangians. You can treat this as a well-to-do quantum effective theory. Okay, you have a Fock space for the pi's. Everything is fine. There is another example, and this is where so as I said, the superfluid is like having a cosmic clock. Notice that a field phi that can play the role of a clock is also what you have in inflation. And in fact, you can view inflation, you can stretch inflation as this sort of superfluid where you have explicitly broken the internal symmetry. Instead of being exactly flat, it's only approximately flat. And in fact, there are models of inflation like known as ghost inflation, where you precisely deal with a superfluid, okay? The general sort of superfluid. So that's a relative of inflation. Let me come to the fluid instead. Oh, the fluid, or if you want also the solid, it arises when you have a different situation. Rather than having one scalar field with a shift symmetry, you have three scalar fields with a shift symmetry. And again, you have solutions that depend on coordinate. And with these three scalar fields, we are in 4 dimensions here, okay, 3 + 1. With these three scalar fields, you can imagine backgrounds where each different scalar has an expectation value along one of the 3 directions, one of the 3 axes. And again, so you have three fields, 3 expectation values, and 3 fluctuations, 3 fields that represent fluctuations. And so in this situation, in the background, what these phis are essentially rulers. Before you had the clock, and now you have rulers. So here, wherever and whenever on the background, the question of where you are is answered by saying what is the value of the fields phi are. Okay. And again, you can imagine the situation, you can imagine having additional symmetry, for instance, some discrete rotational symmetries among the phis. But even without those, the system defined by this situation, again, it's a breaking, it breaks a Poincare to some homogeneous situation. If there's no additional internal symmetry rotating the phis, is not isotropic. But if you have an internal, imagining having some internal rotational symmetry between the phis, then that internal rotational symmetry and ordinary rotations are broken diagonally, are broken to some diagonal group, and you still have some isotropy. Okay, so that very much depends on that. So if you have no internal additional symmetry, what you have is essentially a solid, a non-isotropic solid, and you can make it more and more isotropic by adding additional discrete rotational symmetry subgroups of SO3 or even the full SO3. That will give you a solid. And that again is this is a way of describing, if you want, the theory of a relativistic solid. So, but you can think of a situation where this internal symmetry is further extended. Okay, you can imagine a situation where the internal symmetry actually is extended up to be the full volume preserving diff, internal volume preserving diff. In other words, you can imagine a situation where this phis, in addition to being shift symmetric, is invariant under all reparameterization of phis that respect the volume. Okay. Well, it turns out that with this additional stronger symmetry request, what you obtain is the Lagrangian that describes a generic relativistic perfect fluid. Now, this was discovered several times. I mean, the Lagrangian to describe perfect fluids was discovered several times. I think in the relativistic context, it goes back to this. It was rediscovered in 1973. And also in my paper with Dubosky, Gregoire, and Nicolis, we rediscovered it in 2005. It also happens that I've read somewhere that Lagrange thought about writing a Lagrangian for fluid, and he wrote that in some rendiconti dell'Accademia Reale di Torino, something that I should be able to find, being Torino in my region in Italy, but I haven't yet seen. So it could be that there are even videos. Examples of that. Anyway, this is not new. Now, what the story is here, well, okay, I'm just playing by the rules of effective relativistic field theory. Okay, I have a symmetry. I have a symmetry breaking. Okay, here I have Poincare times this internal S diff broken down by this expectation value phi I equal xi to ISO3, translation, rotation, and also time translation. Okay, time translation are unbroken. So this is a medium that breaks Poincare down. So how do you write the most general effective Lagrangian? So you form at the leading order in the derivative expansion, you form this invariant. Okay, this is the Lorentz invariant object. You call it a meson field. okay? And this transform in a certain way under S diff. If you form the determinant that is invariant, so at the leading derivative order, the more general Lagrangian is just a function of the determinant of X. Again, like before, this function contains all the information about the equation of state of the fluid. And if you consider the equations of motion for the phi's that follow from this Lagrangian, and you consider the form of the energy momentum tensor, yes.
Why determinant is the only possibility?
Yeah, this is the only possible
How
thing.
about trace?
Trace is not invariant under volume preserving diffs. Yeah, trace is not invariant.
Volume
You
preserved.
could even, yeah, volume preserved.
That's what.
As the, yeah, volume preserved. Didn't I say?
No, I just didn't,
yeah.
I missed that.
You could imagine instead of S diff having SL, SL3, for instance. Okay, then you would accidentally you would have the whole thing at the leading derivative order, but the next order in derivative you would break it. Okay, so this system contains the same information as the relativistic fluid that you find in books like in Weinberg 1971, Gravitation and Cosmology. So the equation of motion of the phi's are equivalent to the you can state them also in terms of the conservation of the energy momentum tensor written in terms of rho p and the velocity. Okay, and there's a curiosity about what is the implication in this formulation of this volume preserving diff symmetry. You have a symmetry. You must have conservation laws associated with it through the Noether theorem, but it turns out that the conservation laws associated with the volume preserving diffs is just Kelvin's theorem, which states that essentially in no relativistic case, it states that if you compute the integral of the velocity along a closed path, and then you recompute this integral at the time evolved same path, you find the same result. Okay, so the conservation of participants. Okay, so this is the story for the system. Now, but let me forget for a moment the fact that this system is the relativistic fluid that you find in books. I want to take just the attitude that I am exploring unknown, the known. I'm trying to explore the unknown in the space of quantum field theories. So I'm trying to interpret this object as an effective quantum field theory. And what is really interesting and was essentially drove my little obsession about this is what I'm going to show now. Okay. So as I said before, in the case of the superfluid, or even in the case of a solid crystal, you take the corresponding Lagrangian, you expand it in pi's, you have a quadratic term, you have cubic, the interaction are derivative. The quadratic part has some phi dot square, some gradient, there's going to be some speed of sound. So you have just a theory of scalar or of bosonic degrees of freedom. You can interpret, I mean, the case of fluid is scalar. In the case of a solid, there's also a transverse vector component. Never mind. What you do, you have a theory of bosonic degrees of freedom coupled derivatively. So at long wavelengths, they are quickly coupled. So you just treat it with perturbation theory. You have at first order, you have just a Fock space of free bosons, and they interact by weak interaction, and you just put them.
Are you applying effectively gauge fields here?
Yeah?
Are you applying gauge fields?
No, there's no gauge field.
There's no shift symmetry of the pi by DI or something?
I'm not gauging, these are global symmetries.
Your S diffs, if you oppose S diff as a symmetry, there's no residual symmetry of the pi's?
Which is residual symmetry.
Oh, that's strange. Okay.
SD, does it make?
Oh, no, the residual symmetry is of the pi's is ISO 3. So
Okay,
this,
nothing more general, nothing more.
so this breaks this. Okay, I should have. I think I mixed up some slides. I should have had more. But let me see. I have. And that expectation value here, okay, breaks this down to ISO 3 times time translations. This is global symmetries.
SNIP is a very large global symmetry.
Yes.
Does it, are there infinitely many conservation laws?
Yes. You, as many loops you can build.
And yet there's still interesting dynamics?
Yes. If you, it depends what you do with it. Yes.
I think I'm confused by gauge. There's
There's no gauge. Yeah, I haven't talked gauge.
No, in a sense, there's a gauge fixing when you pick a phi and you decide to write it as xi plus something as a fluctuation. There's a gauge
I
choice.
could have had the same thing before with t, right? Ut. This is a solution. So I don't understand in what sense.
Well, I mean, usually in this picture of brain physics, this is you're picking essentially static gauge, and your fluctuation
Look, this
will be gauge fixing.
there's no gauge here. There's a global symmetry, and I'm finding a solution. So then I can act on this solution with the Poincare group, and I will have that for a moving observer, that the expectation value will look like time dependent because simply I'm moving with respect to the rest frame of the solution. There's no gauge.
Do you break translational symmetry?
Translational symmetry is broken, but there exists a subgroup of translational symmetries here, which is, so there is a translational symmetry is phi x goes into phi, say x, let's look only at space. Phi x goes into phi x minus a, but there's also another symmetry, which is phi i, okay, that goes into phi I plus ci. Okay, and on this background, there is a, so let's call it this internal translation I, and this is the, so this is the ordinary translation pi, and the internal translation ti, and there's a combination of the two, pi plus pi, which is unbroken. Okay, depending on how you normalize it, right? There's a diagonal subgroup, there are translations, it's very much like before with time translation. Okay, the superfluid system has a scalar which is as a linear time dependent. So it's time dependent, it's breaking time translation invariant. Yet it's stationary because it keeps going around, and all points are the same because they're related by symmetry. That means that there exists a linear combination of the original time translation and charge rotation that acts. Also, I think this will give you the answer. Yeah. Okay. Okay. So what is really peculiar about this system is that when you expand around the background, okay, so around the background, as I said, there is this symmetry breaking pattern where this ISO 3 is not fully included in ISO 3,1. It's partly here and here. It's like when you have SU3 left versus SU3 right, broken to SU3 isospin in QCD. Here you have internal translations and internal translation and external translation in space-time translation, and there's a linear combination that is preserved. Very much like you have a special subgroup of SDIF, which is rotations, and you have which is rotation acting on the index xi, and you have the space-time rotation acting on the coordinates. There's a linear combination of the two that is unbroken, and it what ensures that the system in its around the solution is isotropic. Okay, that the isotope is preserved by the solution, and because of that, the fluctuations now, which originally had an index and internal index, now they have a genuine rotational index, can be viewed as vectors of the rotation of the program. Okay? Anyway, so they are vectors, and so their action, you expand it, okay, it respects invariance under this unbroken symmetry. Okay, so they're vectors of that symmetry, they are translation. So it starts with a quadratic term, cubic, and higher. And you see, this pi, which is now a 3-vector, can be decomposed, like these are just any with ISO 3, every wave, every field can be decomposed in helicity components. So you're going to have a longitudinal component of helicity 0 and a transverse component, helicity 1 and -1. And what happens here is that the transverse component does not have any gradient energy. Okay? So while the longitudinal component, which corresponds to compressional modes, okay, ordinary sound waves, is a well-to-do quadratic Lagrangian, which you can from which you can construct the Fock space. Okay, just a bunch of harmonic oscillators in first approximation. For the transverse mode, you have no gradient terms. Okay, and that is enforced precisely by the nonlinear realized S-diff. Okay, volume conserving symmetry. So it's not a set of harmonic oscillators. Okay, it's like you have a set of degrees of freedom that have their quadratic action is purely pi dot square. Okay, so this is more akin. It's not like an harmonic oscillator, so you cannot construct a Fock space. It's more similar to the dynamic of a free particle on the line. Okay, free particle on the line, the action is x dot square. When you quantize it, this is not a harmonic oscillator. You don't even have a ground state. Or if you want, you have a sequence of states whose energy is smaller and smaller and smaller that are eventually totally delocalized and non-normalizable. Okay, so but what matters in that case is that the wave function, if you want, of this putative ground state that you can think of asymptotically, is totally spread. It's not localized in coordinate space like for the harmonic oscillator. The harmonic oscillator x dot square plus omega square x square is localized at the origin. Okay, you write everything in terms of Hermite polynomials, and the thing goes down. The wave function goes down exponentially. So it's localized, and that's the essence of our perturbative treatment. Here, on the ground state, these degrees of freedom, the transverse degrees of freedom, they will be totally delocalized in this field configuration space. Okay, so you cannot treat them in perturbation theory. So the question is, so the transverse phonons are not described by Fock space. Okay, so then the question is what to do with this theory. Okay, so how do you treat this theory? So that's So what I want to do now is to zoom into these questions. The first thing to do that I do is to, well, first of all, the problem concerns the transverse modes. Okay, essentially the modes. By the way, at zero momentum, these modes are simply obtained by acting with your at zero time dependence. These modes simply correspond to acting on the wave with the volume preserving diffs. So they are deformations of your original solution just by the action of volume preserving diffs. Okay, and since this is a symmetry, this is a completely flat direction. It doesn't have any gradient energy. That's the origin of this lack of a gradient energy. Is the volume preserving diff. By the way, the existence of modes like this really change the intuitive rules of field theory. Normally, in field theory, we're familiar with the fact that when you go to short distances, when you consider fluctuations or perturbation with wavelength that is becoming shorter and shorter, this also corresponds to going in shorter and shorter time, okay, and going to higher energies. Here, it doesn't seem to work that way. It seems that even at shorter distances, or smaller, bigger k, increasingly large wave vector, you still have at zero arbitrary small frequency, which corresponds to small energy. And the well-known feature of the dynamics, the classical dynamic of fluids, is which is turbulence, is directly related to this. Okay, turbulence is just the fact that you can view it as the fact that you can get a very big vortex motion moving at low velocity, or if you want, low frequency, and this by interacting with the boundaries or with other vortices, it can split into smaller ones, smaller and smaller, or moving slowly, but going to shorter and shorter distances. Okay, you can have at the end you access short distance physics, you even dissipate. Okay, starting from very soft, very large fluctuations. That's the essence. So the reason why I found interesting this is because it looks like this is a setup where UV and IR are not separated like in the standard case. And who knows if we learn something by studying. Okay, as a BSM physicist, I am interested in exploring crazy things. Now, this is crazy if you want, even though it's a very standard field theory. It's just the field theory. So, in order to study how to treat this system, if there is any thing that we can say. The first thing I'm going to do is to just forget about transverse modes. The transverse modes are just standard, okay? And now it turns out that there is a limit, which is called the incompressible limit, okay? It's the incompressible limit where everything moves very slowly, okay? And when the fluid moves slowly, if the typical velocity of the flow is less than the speed of sound, then you don't emit sound waves. So they're essentially decoupled. And so we can take, just to simplify the discussion, this limit. Another way to get to the limit where you forget about sound waves is to take this fluid and compactify it, just to work in a compact space, I don't know, a sphere or a torus. And now the compressional modes, the sound waves, will just give you a Kaluza-Klein tower, okay, with energy going like the speed of sounds divided by 1 over r. You counted the units of 1 over r, where r is the size of the. And so there's a minimal energy in that, which is the speed of sound divided by r. And if your energy is below that, you will not excite it. By the way, the compressional mode do not have the zero mode. Okay, so that's one way to think. So we can think about working at very low energy, whatever that means, sufficiently low energy in a compact space so that we can neglect the compressional mode. In this limit, we can view our system as the mapping between our space, the space of coordinates, into the space of fields. And very much as I did before, I'm assuming this mapping to be one-to-one, okay? If you want, in every point of space, there's one piece of fluid. The pieces of the fluid are labeled by the phi's, so there is some fluid everywhere. And I'm assuming that this mapping remains non-singular throughout the evolution, okay? So no cusps or stuff like that. So this is and up to choosing the right units, can be reduced to a mapping between one space and a copy of itself, okay, in one direction and the other, preserving volume. Okay? This is in this limit, the compressional modes are frozen, so the mapping is volume preserving. So this is the limit that applies when the velocity is small enough, as I said. So this limit is always non-relativistic, okay? And at lowest order, so it must have a small velocity. At lowest order in the velocity expansion, the action is simply what you would have guessed, okay? It's 1/2 times some coefficient, which you interpret as the mass density, times the velocity square. But notice that now the velocity is a non-trivial variable, okay? It's the derivative of, you can view it through the back mapping. Instead of x into phi or phi into x, it is the velocity of the fluid elements, okay? So it's the derivative of the mapping phi to x with respect to t with phi fixed. Okay? So this is the derivative, and this x of phi is a mapping that is constrained. So this v is a constrained variable. This is just to tell you that therefore this is not just a trivial theory, okay? This theory is coupled, okay? It's like a sigma model. It looks at face value as just a quadratic Lagrangian, but it's actually nonlinear. And okay, now with this Lagrangian defined this way, an action defined this way, with v being this variable, you can, of course, these are constrained variable. You can go through the song and dance of Dirac bracket construction, Dirac quantization, okay? But there's no, okay, I'm not going to do that, okay? I just want to, but whatever that will be, okay, you expect this v, which is a derivative of some variables, to give you your generalized momenta, okay? And when you rewrite your Hamiltonian in terms of generalized momenta, very much like it happens for the free particle in your mv square, this rho will end up being in the denominator, okay? So the Hamiltonian is going to be 1 over rho times some expression, okay, written in terms of your generalized momenta, which here I don't even want to write down, okay? So then, once things are written this way, you can start guessing of what you expect for the spectrum, okay? So you have 1 over rho, the spectrum is energy, and what do you expect for the energy levels? So let's consider, for instance, so what do you have at hand? You have rho, you have the wavelength. Let's say you at the non-perturbative level, you will have fluctuations that have a certain momentum k. Of course, this is an effective theory, so it's an effective theory, so there is also some fundamental cutoff scale, call it lambda, which might come into the game, okay? So then the question is, what dependence do you expect here? And there are two limiting situations that you can think of. The first limiting situation is the one where the gap is purely controlled by the cutoff. Okay? So then if you are in n+1 dimensions, this given the dimensionality of rho, this is what you expect. Okay? You expect a gap, you can expect modes with such gap, lambda to the 2 plus n over rho. And it turns out that this is precisely what Landau guessed in his 1941 paper on superfluids. Because I haven't said it, because among the various people who have considered the perfect fluid, well, those cases I mentioned before, they're all classical. But actually what Landau did originally in his 1941 paper on superfluids, he started with hydrodynamics, okay, the equation of hydrodynamics, and he tried to treat them quantum mechanically. Okay, so he tried to derive a Schrödinger picture for hydrodynamics in terms of operators. Well, Heisenberg, if you want, okay, and he immediately got to the problem of these transverse modes. Okay, and it turns out that these transverse modes, when you define them properly, the canonical variables satisfy an algebra, okay, a non-commutative algebra. And then Landau says, well, this algebra is non-commutative. When there are non-commutativity, there's always going to be a minimum quantum of something. And he says, because of that, I don't expect this mode to go down to 0. I expect them to be gapped. And the only thing I can guess for them is whatever cutoff the fluid description has. Okay. So this was his guess. And having made this guess, he got rid of the transverse mode that you have in ordinary fluids, in all ordinary fluids. It was only left with the compressional mode, which is precisely what you have in a superfluid. You only have one compressional degree of freedom. Vorticus motion is associated with singularities, the vortices of superfluids. But in terms of soft modes, there are only the compression. I don't know whether the fact that the data of Kapitsa had influenced his guess. Okay, probably did.
What is this lambda to the power 2 plus n divided by rho? That is the
Some short distance.
Is it the symmetry breaking scale for S?
No. This is, I mean, this is an effective field theory.
So lambda is the cutoff.
Yes, the cutoff is the inverse
What
cutoff.
is lambda to the power 2 plus 1 divided by rho?
This is energy. This is energy.
That is some kind of a gap for that.
Yeah, this is the gap for the additional nodes. And I think he has this formula. It's as lambda to the 5th over. In this case, n was 3. He has lambda to the 5th over rho. Okay. Now.
And what is this kappa to the power?
Now, okay. Then there is the extreme other option that you say no. It could be that instead this gap comes from calculable infrared effects. Okay, and they will be associated to the only infrared parameter that you have for these modes, which is their momentum. Okay, and again, then by dimensional analysis, you imagine something like this. Now, this is for n equal 3. This is a lot softer than omega equal k or a k squared that we're familiar with. But still, it restores the so-called relation, the relation that if you go to bigger momenta or if you go to shorter wavelength, the energy will increase. Okay, and this is what we were guessing. This is in a sense, of course, I haven't done any computation. I'm just doing dimensional analysis here. This is in the sense bullshit, if you want. This is just. Is this clear? It's just dimensional analysis. I am not doing any more. And this was what we were guessing in 2010. But of course, there are intermediate possibilities. Okay. And what I want to now do is to try to compute this thing. Okay. No, in order to do that, I will focus on the simplest possible situation, simplest possible non-trivial situation. So normally, if you want to understand the quantum field theory, the first thing you do, you go to the lowest possible dimensionality. We understood a lot about notability and cage theory because in 1+1. Here, 1+1 is not good because in 1+1 you don't have any transverse modes. Okay, the first dimensions where you have transverse mode is 2+1. So I'm going to 2+1, and then again to cleanly eliminate any influence of the compressional modes, I compactify, and the simplest thing to do is to work on the torus. Okay, so what I will be considering is an incompressible fluid on the two torus. Okay, and in the same way I was explaining before, the up to choices of units, the dynamical variables are just the mapping between the original space, which is the two torus, into this fluid space, which is also two torus, and backward. Okay, so it's x5d, and so at every given that these two spaces are essentially the same, they are the same space. Okay, so and this mapping is volume preserving. The configurations that the system, let's say classically, goes through as time passes are simply simply correspond to volume preserving mapping of the torus onto itself. Okay, so the set of volume preserving mapping of a manifold to itself is a group, is S diff. Okay, so even in this case there is an infinite group, but this is simply to tell you that what this system is. This system is just a point moving in time on the group manifold. Okay, and the group manifold in this case is volume preservative of the torus. So the evolution of the system is simply motion of the group manifold. Now, this sets a very inspiring analogy between this system and other examples of this type. Okay, and we have a name for these examples. We call them rigid body. Okay, or generalized rigid body. So what is a rigid body? Okay, so a rigid body is a potato. Okay, take a potato, and how do you characterize the position of the potato? Well, you take three toothpicks, you insert them at 90 degrees respect to one another. We are Cartesian. Okay, so and the configuration of the and then there is an experimentalist who has some very well-grounded reference frame in the lab, and the configuration of the potato is simply given by the rotation matrix, the SO3 matrix that maps the toothpicks reference frame into the experimentalist reference frame. So again, it's a group element, not S diff, smaller group SO3, but the time evolution of the potato is simply a motion in the SO3 group manifold as time goes by. Okay, and so it's characterized by matrices with two indices, a bar indices which refers to the reference frame in the lab, and a non-bar index which refers to the potato. Now, this analogy is I think it was first pointed out and developed by Arnold. Okay, in an article in the 60s, and it's also featured in his mechanics book. And I learned it from. I mean, I really like this book, but I never read this part before, and Slava Richkov pointed out to me this, and that was a damnation because it was what put me on this project. Okay. So there is this parallel, and the parallel goes and this parallel will be crucial in what I will do next. I think I'm really slow. I don't know why I'm being so slow. I normally, yeah, I don't know why I'm being so slow. I am super slow. Maybe I'm too apologetic. So anyway, just very quickly, in the case of the rigid body, you can think of two ways the SO3 acts. It can act on the left. Remember, alpha bar of the index of the experimentalist, which just corresponds to changing the reference frame of the experimentalist, changing the point of view. Okay, that's a symmetry. But you can also act on the right. You can think of acting on the right, and this simply amounts to placing the three toothpicks in a different orientation with respect to the potato. This is not a symmetry, as long as the potato is a bad potato. Okay, so these are the equivalent way of parametrizing the position of the potato. You can do the same thing for the fluid, okay? Remember there, the dynamical variable is this mapping, which is a group element. And you can act, now here, the group action is function composition. You can act with volume preserving diffs, either on X or phi, okay, in this way. And here I was calling left what is really the left, here right what is really the right. But actually, in this case, I will reverse the notation. And the reason is that what is left is the symmetry, the transformation level left is the one that is really a symmetry. And the action of volume preserving diffs on phi is the original symmetry of our Lagrangian, so that's really a symmetry. On the other hand, volume preserving representation of ordinary coordinate is not the same, in very much the same way, but is reverted. So again, here you can think very much like for the rotating potato of a doubling of the symmetry, left and right, one is a symmetry, the other is not. And this characterization goes on when you consider the dynamics, okay? Now, the rigid body is simply the 1 + 0 version of a sigma model, where you have a group G, in this case SO3, broken down to the identity, okay? And the degrees of freedom are just the Goldstone bosons, or the angular variables associated with this breaking. And if you remember the physics of the rigid body, it's most conveniently, the dynamics is most conveniently written in terms of the angular velocities or of the angular momentum or the angular velocity referred to the body frame, okay, axis, okay. So it turns out that the angular momentum projected on the body axis up to a sign is just the generator of this non-symmetric right rotation. It just corresponds to the rotation of these toothpicks on the potato. Okay, is the SU2 right generators, and the Hamiltonian, okay, is just this quadratic form, and the time evolution of the angular momentum and these R satisfy precisely the algebra of angular momentum. It's again is the right action of the group. This is the reason why, and their time evolution is completely fixed by the algebra. This classically, quantum mechanically, of course, you could also do it at the level of Poisson brackets, but let's do it quantum mechanically. Quantum mechanically, the system, how do you construct the Hilbert space and the energy levels? Well, the Hilbert space in the case of the rigid body is given by the complete set of orthonormal wave functions on the group manifold, which according to the theorem, the Peter-White theorem, corresponds to the following. Take all possible representations of the group, which in the case of SO3, they are labeled by angular momentum L. For each of these representations, consider the matrix that represents every group element. Every matrix of this representation is going to be a 12 + 1 times 12 + 1 matrix with elements that depend on the three Euler angles. Okay. Now, take all the entries of each representation and all these and take it for all the possible representation. This set of functions is a complete orthonormal set. So the states in the Hilbert space are simply associated in one-to-one correspondence with the entries of all possible representations. So the Hilbert space structure is simply a direct sum over L, over all representations of these 12 + 1 squared wave functions, okay, corresponding to the entries of the matrices representing the group elements. And on these matrices, again, since they are elements, they represent SO3, you can act with the group to the left and on the right. So they correspond to L, L multiplets of SU2 left, SU2 right, SO3 left times SO3 right. Okay, and again, you can now computing the energy levels. Okay, only requires studying the algebra. I mean, for every representation, these matrices R will be 12 + 1 matrices. Okay, and in each block, finding the energy level simply amounts to replacing the R with the corresponding generators in that block. Okay, it's simply the 12 plus 1 square generators of, representation of the generators. Okay, and you will get 12 plus 1 levels. Okay, in general, they are non-degenerate. Okay, because this is not a symmetry. On the other hand, all these R's commute with the left action, which corresponds to rotating the experimentalist. And so each energy level will be 12 plus 1 degenerate. If you want, the left action corresponds to rotating the experimentalist, or if you want, rotating the body and all its velocities, that you get an equivalent motion. While the right action corresponds to rotating the total angular momentum with respect to the body. Okay, you can keep the total angular momentum fixed, but it can have different orientation with respect to your potato. If the potato is like this, it could be like this, it could be like that. And while the states have the same angular momentum, they will have different energy. Now, the situation in the case of the fluid goes along the same way. Sorry, I have a real time problem. I think I don't know why I went so slow. I went slower than anywhere.
Do you have? How much more?
If you give me 10 minutes, I can try to finish in 10 minutes. Yeah? Okay, so the situation is completely parallel in the case of the rigid body. The analog of the R generators is given by the vorticity. Okay? The Hamiltonian is given by, which is V squared, you can write in terms of the vorticity. Okay? It's like vorticity density with a Coulombic interaction. The evolution, the fact that R is not conserved corresponds to the fact that R is only convectively conserved, and it's very similar to the time derivative of R in the rigid body. Okay? And the dynamics, classical or quantum mechanical, whether you do commutator or Poisson brackets, is simply given by the algebra of this R. Okay, and the algebra of the R is very much like in the rigid body. They were satisfying the algebra of SO3. Here they satisfy the algebra of SDiff, which in momentum space, if you take the Fourier transform of this guy, you go to momentum space, takes this form. Okay? So essentially, the fluid is like a rigid body, is a generalized rigid body, where instead of SO3, you have the volume of SDiff. But by the way, even in this construction, the fact that here that I have SO3 is just convention. Here, this alpha, it could be any other group, could be SUN, could be whatever you want. They're just generalized notion of rigid body. Okay. So between the ordinary rigid body and the fluid, there is a lot of other systems that fall in the same category. Then, point particles moving on the Coset space, on the group manifold. Again, so here, however, the group is infinite, and the construction of the representation by applying an analog of the Peter Weil exceeds my understanding. Okay, but overall, I would expect to have something precisely in the same way, if I can make sense of it, that the Hilbert space will be a direct sum of blocks which consist of a Q comma Q. Q is going to be a representation of SDiff. Okay, and this double, if you want, the doubling of, if you want, the degrees of freedom has to do with the fact that for every configuration of the velocity, I can act with this SDiff and realize it with different parametrization of the phi's. Okay, so the same velocity I see in the fluid can be obtained by a variety of different configuration of phi's. Okay, so in a sense, this in a sense may be worrisome, because you say there is more than just velocity describing the state of the system. That is called them hidden variables. So you may worry how to go ahead with this. Let me go pretty quickly. There are two ways to look at this. One extreme would be to say, okay, gauge SDiff. Okay, assume SDiff now, I take it as a gauge symmetry, which means that I only consider the states that are invariant under it. Okay, but because of the structure of this double Q comma Q, the only state of that type is the 0, 0, and that is the total singlet, in which there's no dynamics. All the charges are 0, but the charges are just the curve of the velocity, and so the velocity is 0.
And the solution that he started with was not invariant under SC. right? This phi equals X was not invariant under
No,
X.
it was not invariant.
So
I agree, but I can still say that I is like when I have I have a redundant description if you want. The specific solution I'm using is not invariant, but the states I only consider states that are quantum mechanically totally spread. So that solution is not invariant, but quantum mechanically I will have to have a configuration where I have where the wave function is spread over all configuration that I add by adding it with a diff on that solution. See, quantum mechanically, I don't have just a solution, I have a wave function. So in that sense, it's invariant. It's like saying that for the rigid body, the potato is the localized in all possible direction. It's like the constant. So this actually is what Feynman would say is the resolution of the approach of Landau, where you can say that actually the underlying elements of the fluid are made of particles, they're indistinguishable, which you go to sufficiently low temperature. And so you gauge it, you get rid of all the transverse mode, and you get back just the compressional mode, and that's a super. Okay, that would be one point of view. I want instead to continue and see where I get if I continue with this. And then perhaps stop and interpret it. So in what follows, I'll try to really solve this problem, and postponing for later later even after this talk, what's the meaning of this? Okay, if I can extract some interesting dynamics, then who knows? Okay, but by the way, I should say that there is another way. I should anticipate that there's another way of formulating fluids where you don't have this additional S-diff. This is the formulation in terms of Clebsch variables. Okay, I anticipate that, but I will get to that indirectly through this long discussion that I now start, which I have to do in 5 minutes. So how to attack this problem? Well, as I said, this is like a generalized rigid body. Okay, well, it turns out that this is an infinite group, so it's hard to deal with. But as was pointed out long time ago in several contexts, the volume preserving diff of the torus can be viewed as a limit of SUN when n goes to infinity. This construction can be done following Toft. In fact, Toft invented this, okay, originally. Just take SUN, parameterize the fundamental representation, take n to be odd. You can assign labels to the fundamental that go from minus n minus 1 over 2. That. So essentially from minus n over 2 to n over 2. Okay, these integers. What about the bifundamental, if you want, the adjoint essentially, is gonna, its element, you can label them with n square, let's say it's square minus 1, but n square roughly indices, okay? Just fundamental times anti-fundamental. And in fact, Toft has found a parameterization where you can describe the n square minus 1 generators of SUN by labeling them with these integers except at 0, 0. In other words, these are Jn matrices, n times n, they're traceless, they satisfy this relation, and they're a particular basis of SUN, and they satisfy the following algebra. So there is, to get it short, there is a basis of the algebra of SUN where the generators are labeled by integers, excluding 0, 0, going in this range, and the algebra takes this form. I don't need to show you how this is constructed, okay? Only that this algebra, if you rewrite it by choosing properly rescaling the generators, takes this form, where n wedge and bar is really the wedge product in 2 dimensions, okay, of these integer labels, okay, integer labels, okay. So it turns out that while this is an algebra that is not the algebra of S-diff, however, if you take only the tail, if you want the small n and small m tail compared to capital N. So in other words, if you take n going to infinity with little n and little m fixed, then the sign can reduce to the argument, and then you have precisely the volume preserving this. So the SUN rigid body offers a UV completion, if you want, of the perfect fluid. Okay. So now we are unavoidably going to have a cutoff. Okay, and now remember, I'm identifying these generators of SUN with the vorticity algebra, with the Fourier transform of the, I mean, to the vorticity in momentum space. Okay, and that's it. So on the torus, on the continuum torus, these indices we're taking infinite integer values, but now in SUN they take only a finite range of value, meaning the space is also latticized. Okay, because you have a finite number of degrees of freedom, so not only the space is compact, but it's latticized, and the lattice. The momentum, and so in this perspective, these n are interpreted as the wave numbers, the momentum, okay? And the Fourier space is the same space. Okay, and to obtain the spatial dynamics, you simply have to Fourier transform back, and again, we are in a discrete space. You're just doing discrete Fourier transforms. Now, as I said, the interpretation of SUN. The identification of SUN with SDIF with SUN only works in the tail of the algebra for generators that are labeled by small momenta, if you want. So, as I said, this corresponds to a fraction, a small fraction of the generators, essentially n out of n squared, and it corresponds to wave numbers less than square root of n. Now, momentum smaller than something means length scales bigger than something. In this respect, this corresponds to separations on this discrete space that are more than square root of n fundamental lattice sizes. Okay, so it means that the effective description in terms of a fluid can only emerge not at the lattice length, but at some length which is square root of n, the number of the lattice length. So now, as I said, we have an n by n lattice. Our torus is becoming n by n lattice, and this means that we can characterize our n by n lattice in terms of two lattices, a lattice and a sublattice. There is a coarse lattice which is square root of n by square root of n, where the lattice length is precisely square root of n points. Okay, and inside of each cells there are other square root of n by square root of n, that is to say n cells, so that the total number of cells is n squared. Okay, n times n. And it is only on this length scale, which now I can assign the length of my torus to pi r. It's only on this length, beyond this length scale, that I have any hope for this system to behave like a fluid. Okay. So,
question: if one momentum in the x direction is larger than what you accept, it would still work if so you take two elements, one that has large momentum and one that has small momentum. You
can also do this asymmetric situation. Yeah. Yes, we did not consider that. We took if you want, I can tell you how that works.
It resonates a bit with UBIR mixing.
Yes. It's true. If you but the simplest thing is just to cut it off this way. You're right. And so now we have an interpretation for this length. This is what I would call my UV cutoff, the lambda of Landau, if you want, and it is this coarse grain lattice length. Okay, and so on.
So just to be clear, that lambda is the symmetry breaking scale for SDIF. The theory does not have SDIF when you reach that scale. It has SUN for finite n.
This is it's not the symmetry, it's the deformation. I still have a symmetry. I have deformed my group.
Have the infinite dimensional symmetry.
Instead of having a group, it's not that I've broken it, I've deformed it. I've deformed.
Finite dimensional symmetry.
Sure.
Yeah, not an dimensional symmetry.
Sure. Yeah, that's what I want.
This is what I asked her.
Sorry, I don't understand what you're saying. Sorry, I don't. Sorry,
I think I'm just confused, but you can keep going.
I'm sorry to confuse you. I came all the way to confuse you. So the Hamiltonian, okay, as I said, the algebra. So formally, you would write the Hamiltonian by summing in Fourier space. Remember, I had this 1 over Laplacian. In Fourier space is this. It will sum up to infinity. But now I'm aiming at a realistic description. I know there should be some UV cutoff. And I know that the algebra beyond a certain point cannot, if I realize it with SUN, will not correspond to the one of S diffs. So I just cut it off. Okay, I just have the fluid Hamiltonian with only the generator that corresponds to the infrared tail. Okay, and this guarantees that these low line generators will satisfy a truncated version of Euler's equations. Okay, if you want, this is like taking the SUN rigid body with a specific moment of inertia. If you take this and you write in terms of the Toft generators, it comes in this following form. There is an expression which is purely written in terms of SUN matrices or in their representation, and there's an overall coefficient which is precisely the gap that by dimensional analysis you would have now had guessed. Okay, and then the question is now you can compute. Now with this Hamiltonian, you can compute the spectrum and see what happens. And now you go through representations. The first representation is the trivial one, the ground, I mean the trivial representation, the singlet, and then of course everything collapses. You get zero energy that you would interpret as the ground state. Then you go to the fundamental. The fundamental consists of n states. Okay, so what this n state can be? Well, it turns out that you can find a basis of the fundamental in SUN, which on this lattice corresponds to a configuration where vorticity is localized on one of the n, square root of n times square root of n, coarse grain cells. Okay. In fact, the existence of this coarse grain lattice corresponds to the fact that you know there must be representations that have dimension n and not n squared. So they're all you ought to be able to place them on a lattice which has n points, not n squared. You look at this fundamental, you find out that they're all degenerate, they all have the same energy, and it goes precisely like Landau predicted, times a log. And of course, when you have a log into dimension, you already know what you're dealing with. What you have is that the states are localized vortices. If you compute the vorticity just by doing these discrete Fourier transforms, you find that the vorticity, of course, the total vorticity integrated over the volume is zero because it's a total derivative. But it just boils down to a localized delta function minus a smooth background. And when you send the volume to infinity, this becomes really a delta function, just a vortex. And if a fundamental is just a vortex localized at the point, what about the anti-fundamental? Well, the anti-fundamental is the antisymmetric product of n-1 fundamentals. So which means that you will have to play n-1 vortices on this coarse grain lattice, all on different points because you're antisymmetrizing. So basically you place a vortex everywhere apart from a point. And if you look at the flow of a conversion like that, it corresponds to an opposite flow in the remaining hole. So this is an anti-vortex. So the anti-fundamental is an anti-vortex. And you can look at and then you can go on. You can starting all the higher reps, okay, just with Young tableau, and you find that they are all gapped, okay, until you get to the adjoint. And when you get to the adjoint, something interesting happens because the adjoint is a product of a fundamental times an anti-fundamental, okay, and this product, it's contained in that product. And but in that product, there's also a singlet, okay? And what is the singlet? What the singlet is, you pictorially you see it this way. You place a vortex here, an anti-vortex there. Then you go to the other point and you do the same. So in other words, the fundamental is an entangled state where on each coarse grain lattice side, you put a fundamental and anti-fundamental and you sum over. And this has energy zero because it's the fundamental. It's just equivalent to the fundamental. And but you see, you can imagine locally doing this in an imperfect way with a smooth exponential modulation. Locally it looks the same, but globally is not a fundamental, it's in the adjoint. And naively, you think, I mean, intuitively, you would expect that given that locally they look the same, also their energy should become increasingly similar in the limit when you send the volume to infinity. And in fact, what you find is that in this class of states is not gapped. Okay. And in fact, what you find is that there are two ranges when the vortex and the configuration in the adjoint where essentially vortex and anti-vortex are almost placed on top of one another, and these are not gapped. While these ones, they really behave like vortex and anti-vortex, be separated and have a gap that grows like Landau predicted times a log, while in this other case, you get a quadratic gap. So you get a combination between the expectation of Landau and the naive expectation that the gap goes like purely in terms of P. So it's lambda squared P squared. So these behave like slow-moving non-relativistic particles. So what are these particles? As I said, these particles are essentially bound states of vortex anti-vortex placed almost on top of one another. Okay, and in fact, as you know, what is the momentum? When you place them really on top of one another, the momentum is zero. They cancel one another. Okay, and their motion is propelled. One propels the other intuitively. Okay, so their momentum is proportional to their separation. And in fact, what you find is that these vortices are just quanta that carry a vorticity dipole. Okay, and the dipole grows linearly with the momentum accordingly. So since we have objects that propagate and they have a ungap dispersion relation, you can start asking yourself, what about scattering? And scattering, it turns out you have to study, oh shit, I really went. Tensor product of adjoints. Anyway, to make a long story short, it turns out that in the space that is made of a product of two adjoints, well, you can either do this the symmetric or antisymmetric product of adjoints. And in each of these subspaces, you can describe time evolution in the limit where n goes to infinity and the volume becomes infinite in terms of effective EFT, or some effective theory with suitable degrees of freedom. And the effective theory, which we call the Vorton EFT. Okay, so in the bosonic sector is something like this. Okay, where this is the original interaction. Remember, these Vorton fields, which are just scalars, canonical scalars satisfying ordinary commutation relations. So this is precisely the vorticity. This is vorticity 1 over Laplacian. Okay, and this is the Lagrangian. Of course, the Hamiltonian this disappears. It's just that, and that's it. Okay, and you get this result. For instance, this is a peculiar EFT with peculiar scattering amplitudes. So, for instance, in the bosonic sector, it's convenient to write the initial and final states in this way. You find that the scattering amplitude in the bosonic sector is S wave, but it has the funny peculiarity related to this dipolar interaction, because these are interactions through dipoles, that the scattering amplitude vanishes when the two vortons cross one another at 90 degrees. Essentially, this is like the perfect New York traffic crossing, okay, where avenues and streets do not see each other. In the fermionic sector, you get other funny properties. Okay, for instance, if you scatter two vortons which have the same energy, the final states, while kinematics allow to have parallel final states, parallel momentum final states, this specific amplitude has zero probability. So, so at the end of the day, you have a specific quantum field theory with very clear signature, and the amplitude is controlled by just the density rho. Okay, so this is the sense. It's like the pi of Lagrangian, where you have a scattering amplitude controlled by f pi. Here, the rho is explained by rho. So, so let me summarize. There are more things I could say, but I'm already amply over time. So this is what I've shown. So the quantum flows in this system are simply they correspond to the study of SUN matrices, okay? And it turns out that all the representations that represent Zn of SUN non-trivially are gapped, while the representations like the adjoint and product of adjoint that do not represent Zn, that for which Zn is trivially represented, are ungapped. And this we call vortons. And the question is, just to see whether this all makes sense, is it possible to realize something like this in a lab? Or in other words, is this a new universality class of 2 + 1 dimensional field theories one can think of, or not? Thank you. Sorry.
Before I take questions, maybe those who may have to leave, feel free to leave. And those who have questions, please go ahead.
Sorry, guys, it's an embarrassing. I won't make it too long. Sorry.
Is there a way to interpret the Young tableau in terms of the fluids?
Yeah, you can interpret the elements, the box in the Young tableau in terms of vortices, because this is the fundamentals, right?
And like
and how you symmetrize the vortices. Yeah, but of course, if you go higher, so this interpretation in the product of two adjoints in terms of bosonic and fermionic, okay, it works for the product of two. If you start having three, then you have more representation than just, you don't just have symmetry and antisymmetry, you have all the representations of the permutation. So this doesn't look like ordinary, it looks like distinguishable particles. So that is because you have these internal degrees of freedom. Now, however, there exists an alternative formulation of hydrodynamics, okay, which is in terms of Clebsch variables. This is, for instance, discussed, well, was discovered by Clebsch. I don't know whether he wrote it, but there are several papers by Jakiv, Nair, Polychronakos, P, where they discuss it. That's, again, it's a theory, it's in 2 dimensions. It's a theory not of 2 scalars, it's a theory of 3 scalars. Okay, it doesn't have that volume preserving diff I started with. It doesn't have that VEV that depends on position I started with. It doesn't have this S diff. One of the fields is a time, it looks more like a superfluid because one of the fields is a linear time dependence, plus 2 other degrees of freedom. That Lagrangian, if you, of these bosons, if you take it in the incompressible limit, gives precisely the Barton theory. Right? However, the problem is that Lagrangian is fixed by yet another volume preserving symmetry. It is not this one we started with. It's a sort of dual volume preserving symmetry. And but however, that's realized in a different way. And but it's not clear, and this is where we got confused in the project 2015, how this symmetry makes sense quantum mechanically this way. Now, because when you write the theory this way, you see, these phi's are not gapped here. There is, if you go to the Hamiltonian, there's purely a quartic term. The K-square dispersion relation comes when you normal order this interaction. Okay, and this normal ordering is UV divergent because if you take it as an EFT, so the SUN, I see the SUN construction as something that assures me that there exists a bigger construction where you don't worry about UV divergences. By the way, notice that this theory, if you compute, see, this is the amplitude, but the amplitude is not precisely the scattering phase. To get the scattering phase, which is what measures how strong the interaction is, you have to normalize the states suitably. If you normalize them suitably, you find that the scattering length, the scattering phase goes like p squared over lambda squared. So rho disappears there. Okay, it goes like p squared over lambda squared. So it means that at the cutoff scale, these guys are strongly coupled. So unless I have but the effects that guarantee the presence of propagating fields, because otherwise these guys do not even propagate, is precisely the normal ordering here, but is dominated by a scale where the theory is strongly coupled. So it's a theory, it's an effective theory that is not sufficiently effective because you still need UV effects. And the SUN buys you some crappy, no matter how crappy, okay? Maybe it's a Baroque construction, but it's a construction where there exists a story based on symmetry, a certain symmetry, SUN, it's finite, whatever, where you follow just the rules of the rigid body and you get down to this. So now it turns out that also, and this is something I'm doing now with Gabriel Cuomo and my student Eren Fiora, you can apply the same SUN regularization also to the other Clebsch construction in a different way. So this is just to say that, so we got to this Lagrangian in perhaps this long winding way, but there was a shortcut to that. But I only appreciate that after getting there. Okay, so that's
You're not worried that the Lagrangian is non-local?
Well, I mean, you can always localize this Lagrangian by adding. So first of all, there's no locality if you start from the Clebsch construction. It comes from integrating out the compression alone. Okay, so the original Lagrangian that you start with is only when you decouple the sound is becoming local. So and you see it nicely in the Clebsch construction. So essentially you integrate out the sound offset. Okay? In the limit where the time derivative part doesn't matter, you only have one over Laplace. So, sorry guys, I really want to. I don't know, you were worried about sorry, I don't understand.
No,
Seven.
I think it's a different, very similar kinds of regularization show up in many contexts, say in string theory. And
Sure, this started from membranes.
from memory, yeah.
Yeah, but the problem is that membrane people, they never, so I can say, oh, what you're doing was already done. But you see, all these other regularization, they were taking this algebra, and then they would say, oh, this is the S-diff algebra, but then they were not taking into account that it's not S-diff algebra, because it's the S-diff algebra only in the far infrared. So they were throwing, essentially, they were replacing S-diff with SUN. That's not enough, okay? Because then that's not the same algebra. It's only in the tail that it's satisfied. So then you're forced to introduce this intermediate scale, this coarse grained lattice. Okay, and now this coarse grained shows the difference between the separated is precisely the scale that separates between vortices that are vortices and the vortices, and these vortices which are essentially vortices on top of each other. So you could ask, if I have a superfluid, so if you take this vortex and the vortex separated, these are really like vortices and superfluid. Very well separated. But in a superfluid, when you get them closer, and closer, then you say, oh, both they annihilate. Okay, this construction corresponds to a situation where they keep going, and there are states which have essential vortex and vortex on top of each other. Right? So you see also how peculiar it is with respect to things that we know exist. In fact, you can realize these vortons in 2 + 1 QED, or you can realize something that looks like the vortons in 2 + 1 QED by considering a 2 + 1 QED in a magnetic field, okay, where the electric field now plays the role of the velocity, because the Gauss law is the vorticity, so the vorticity density is the charge density. And now what are the vortons? The vortons, something that looks like the vortons are bound state of E plus E minus. Okay, of course, there's an overall rest mass there. Let's forget the rest mass for a moment. Let's forget the rest mass and consider a bound state of E plus E minus in this external magnetic field. Okay, so they form a bound state like a hydrogen atom of E plus E minus. And now, in the ground state doesn't have any dipole, but if there's at rest in the magnetic field doesn't have a dipole, but if you give this bound state a velocity, okay, in the moving frame of the bound state, there will be an electric field, and the electric field will split the plus E minus and generate a dipole. It generates a dipole that is orthogonal to the velocity, to the momentum. That's precisely what the vortons have. And if you work identifying, so the binding energy is E squared, and if you identify the two length scale, which are the Bohr radius and the Landau level area, okay, which is 1 over EB, if you identify all of them with lambda, then you match precisely everything, including the scattering amplitude. The scattering amplitude is simply the scattering of two bound states that scatter with the dipolar interaction. Okay, it depends on momentum. Now, why is this theory not the right one? This theory is not the right one. It's because in this particular theory, in addition to these interactions that are dipolar, and which in the end they give you amplitude that are proportional to momentum, these guys are atoms. So atoms also have hard scattering without any derivatives, right? So there's going to be, I expect that if I describe this in terms of the phi's, there's going to be a term like phi dagger phi square, which represents an S-wave hard scattering. So in that sense, only if I can prepare states such that these guys never overlap and never get very close, I can match what I had before. So it's not yet clear to me. So this, in a sense, suggests that perhaps a system like this is hard to engineer in reality. So I don't know. That's an example of a system of this type.
Maybe you could supersymmetrize this.
Eh?
Maybe you could supersymmetrize this to make it soft in the scatter.
Oh, you're saying you eliminate the potential.
Yeah.
The good thing about supersymmetry is not that it makes things soft. Supersymmetry makes things flat while they're not soft. Okay, supersymmetry allows to have quartic interactions, keeping a flat direction. So it's not making things. So it's not make things soft. You need derivative interaction. You need really goes to both. Yeah.
PPS objects only like derivative.
Well, then you start. Yeah.
Yeah, which is roughly what you want.
Maybe. Yeah.
So I just want to follow up on this comment. So can we consider this kind of fluid, which is supersymmetrized? And how can you characterize all this
No,
this
I have-
object by volume precision?
I imagine, by the way, first thing, supersymmetric fluids, we have all been working on supersymmetric fluids all our lives. Because what is spontaneous supersymmetry break? It's just a field that has a theta-dependent value in superspace. So it's like here I have a phi that has a value that depends on x. Supersymmetry breaking, starting from phi Heliopoulos or Hafferty, it's just superfields that have an expectation value that depends not on x but on theta. So it's a fluid in superspace. So now, so that's already exists, and the sound wave of that is the continuum. The analog of the sound wave is the so. It's only that it's the supersymmetric algebra broken down to Poincaré. This is what we normally do. Now you're asking now another variety. You take the supersymmetric superspace. Yeah, you can find all sorts of intermediates. Yeah, I haven't done it, but I can imagine doing it. Yeah, I certainly imagine doing it. So far, we only did superfluid that are in the theta direction or in the x direction. Now you can start having things that are both theta and x. Is it clear what I'm saying?
Is there a quantum Hall interpretation of your Q squared dispersion relation?
Yeah, the quantum Hall is very much related to this 2+1 where vortices are, right? Yeah,
And it's the same algebra. So.
The same algebra that, yeah, I'm confused on that. So this system, I started thinking about it when I gave a talk in Hamburg when there was the Hamburg Prize for Valery Rubakov, and I think Sergei Dubovsky pointed out. I mean, in fact, we were discussing. You could imagine having two vortex systems, okay, two different systems with Landau levels that are coupled, and they give this like a layer and. But then I thought, yeah, I can really do it with the same system. But this has this hard scatter. So maybe that one allows to have this softness. Yeah, I'd be very happy to discuss that. I'm not, I tried to get information of the Landau, the quantum Hall community, but I haven't yet been able to get the right, maybe you can have. This I don't know yet. I don't know. Yeah, in all these cases, the thing was the HMOs, their emphasis was always on this. Apart from the case studied by Wigman, where he has macroscopic vorticity, right? He has really a lot of vorticity, while I'm starting from a state that has no vorticity, but I have just these little fluctuations. Yeah, for instance, the contact between what it does and what I'm doing here is not yet clear. This would have been nice to have in around.
If not, Ms. Riccardo again.
Sorry for biology.